Okay, we're going to start Unit 5 today. I put the calendar on in your packet as well, so next page. Okay, just going over the calendar real quick here. We're really going to spend the whole month in this unit. But we're kind of breaking it up into two parts here. We'll have 5.1 to 5.3 between this week and next week. And then a couple of days for quiz review. And then we'll have a quiz after we get back from our extended break. And then we'll cover the remaining sections: curve sketching, derivative graphs, optimization, and then have that Chapter 5 test at the end of this month. Okay. Okay, so 5.1. Okay, sorry it's taking so long for me to grade your Chapter 2 test, but I should have that in the gradebook by today, and hope to get back your test, if not tomorrow, then Friday. Okay. And then hopefully over the long weekend, I can get that relay rates turned around, graded as well. Okay, so first, let me just define just go over some definitions here. First, extrema means maximums and minimums, basically the highest and lowest points. So we have something called a relative maximum, relative minimum.
Sophia is coming too.
Okay. And relative maximum here. So basically, relative max and relative mins are basically hills and valleys of a graph. So if you can imagine something that resembles a hill or something that resembles a valley, that is what we call a relative maximum or relative extrema. Okay. The reason why we call it relative, sometimes even you see the word local, but typically we use relative, is because this is the highest point relative to the immediate points around that location, right? So in this local region, this is the highest point. And this is the relative minimum because within this local or this relative region here, relative to this lowest point here, there's no other point lower. And this point is also a relative maximum because it's the highest point in this region, but it's also the highest point overall in the entire graph. So we call this both a relative maximum and an absolute maximum because there's no other y value that's higher than this point on this graph. Okay. So when we have a closed interval, that means the graph is defined at the endpoints and that there are no breaks along the graph. Okay. We call this a relative minimum because it is the lowest point within this region, but it's also the lowest point overall. So it fulfills relative minimum requirements, but it's also the absolute minimum. Now this point here is the absolute maximum because it's the highest point on the graph, but it's not a relative maximum because
the point range. So.
Well, because it doesn't look like the hill of a graph, right? There's no point to compare with on the other side. So it needs to look like a hill or a valley in order for us to call it relative max, relative min. Now, on the open interval, that means we have an open circle. That means the point is not defined, but it will get infinitely close towards that point. Again, this is a relative minimum and an absolute minimum, but there is no absolute maximum because if I try to pick a point really, really close to that value that's not defined, I can always, let's say there's a hole at 5, right? And I chose 4.999 to be what I think is the absolute maximum. I can always pick a point even closer, right? So I can't not pinpoint a single decimal value that's highest that I can reach, because I can get infinitely closer towards that hole. So if it's not a physical point, then we can't define an absolute maximum. Same thing here. You see this arrow? This arrow tells us the graph is continually going down. So there is an absolute maximum here, but there is no absolute minimum, because negative infinity is not considered a real number. So we don't think of that as an absolute minimum. Yeah, over here. Holes and plus or minus infinity cannot be considered as absolute extrema.
There's no absolute maximum in that open interval because there's like a hole there.
Because there's a hole there, right? Okay, so I'll go over this in more detail on the next page, but here's a brief introduction here. Extreme value theorem says that if a function is continuous on a closed interval, so we're going to talk about conditions for theorems. And remember, we've been using IVT, and the theorem for IVT is continuous on a closed interval. Every theorem from here on out, there's always that condition of continuity. So if my function is continuous, then it's guaranteed to have both an absolute minimum and an absolute maximum on that interval. So if my graph is a closed function and there are no breaks, I am guaranteed to find an absolute minimum and an absolute maximum somewhere along that graph. I guess there's one condition exception, and it's what if I have a horizontal line? Then this y value in this case would represent both the absolute max and the absolute min. Okay. So typically the graphs that we're dealing with are not like this. It's usually has some curve to it, and we can always find an absolute max, absolute min. So what if we were unable to see the graph? Then we can identify the candidates for absolute max and absolute min from critical numbers and at endpoints. Those are the only potential places where the highest and lowest points could occur. So we have an endpoint here. We have critical points here. So endpoints are obviously the ones that are, they'll be given to you. They're always going to be the ones that bookends your graph. And then critical points are places where the derivative of the function is either 0 or undefined. So we're going to find f prime, and from f prime, we're going to be able to locate these critical points. And then after that, we're going to insert them all into the original function and then ask the function to tell us which is the highest and which is the lowest y value. Max and min values refer to the y values on the graph. Okay, so let's go through these examples on the back and kind of show you the process of going through these steps.
You didn't draw a graph of these people.
I'm sorry?
You didn't draw a graph yourself.
Yeah, we're not going to draw the graph. We're going to rely on derivative and this process to find the highest and lowest points. So we're obviously, if we can see the graph, it's easy, right? Okay, that's the highest, that's the lowest point. We're trying to do this without the use of a graph and relying on a bit of a derivative information to help us get there.
Are you calculator for this stuff? Or?
Yes, you'll get a calculator. Okay, so confirm. So the first thing is we always want to confirm continuity on a function. Okay. So the steps that we're going to take: confirm continuity. Second, find critical points. The endpoints will be provided for you, so we just have to save that for the end. So the way we find critical points, we find f prime, and then we set both the numerator and the denominator of f prime equal to 0. And the reason why we also consider the denominator is because if there's a sharp turn, that is still a potential minimum of the graph, right? So we have to make sure that we locate all of our candidates. Okay, so once we find our candidates, make sure that they are inside the interval. Then we plug them all into the original function. and then we just compare. Highest y value will be your absolute maximum. Lowest y value will be your absolute minimum. All right, so let's look at example 1. Okay, find all critical numbers for each. What are the values of the absolute extrema? So first, do we have any issues with continuity here for example 1? Okay, this is a polynomial, right? No breaks, no holes. Basically, you're looking for a denominator. If you don't see a denominator, you're pretty much going to be safe. No issues there. But we have to make sure we state our condition. So our first step is to say our function is continuous on the closed interval from 0 to 2. Even though this function is continuous everywhere, we want to just specify the region that we're talking about. So just from 0 to 2 is all we care about. So these are the endpoints. We know we're going to consider endpoints as a potential place where absolute extrema could occur, but we're going to save that and try to find more candidates. So candidates come from f prime. So let's find f prime. The reason why we look at f prime is because f prime will tell us where a slope 0 or a slope undefined occurs. And a slope 0 and slope undefined could lead us to a location where it could end up being the highest or lowest point on the graph. Okay, so f prime. What's the derivative here? Power rule.
12.
Mhm. Okay, there's no denominator, so we don't have to worry about denominator equal to 0, but we're going to set the numerator equal to 0. And this will help us find locations where the slope is 0. Okay, so we set f prime equal to 0. We're going to look for our critical points. I can factor a GCF out. X squared is my GCF. What's left inside?
X.
X minus 1. Okay, so we have two potential critical points. We'll set them both equal to 0 separately. Divide by 12, take the square root. I'm still end up with 0. And x equals 1. So is 0 anything new for 1 that we have to test?
Yeah.
So we already have endpoints, and it's just duplicate. So we look at it. We don't have to include it as well. It's already included in our candidate. Is 1 new?
Yes.
Yes, it is. And is it valid?
Yes, because in between two.
It's in between. Good. So we always want to make sure that our critical points land inside the interval. If no critical points land inside the interval,
No
then
solution?
sorry.
Is it no solution?
Well, there's no solution from the critical points, but we still want to test the endpoints. So if you don't find any critical points, you can still continue with extreme value theorem. It's just that you only have 2 candidates, only the endpoints to test. So it's okay if you have no critical points and 2 endpoints. You still can find absolute max and absolute min. So now we're ready for our, what we call this, the candidates test. So we're going to enter all of our critical points and endpoints into our function and then gather the y values. Right? Highest y value will be your absolute max. Lowest y value is your absolute min. So we'll do f of 0. We'll find f of 1. And we'll find f of 2. 0 and 2 are our candidates because there are endpoints. 1 is a candidate because it's a critical point. Okay, we insert them into the original function because we're now asking for location. So 0 in for x, we get 0. Plug 1 in, we get -1. Plug 2 in. Yeah, so 3 times 2 to the 4th. 24. Yeah, so 48 minus 32 gives us 16. So what's the highest y value that you see?
16.
That's your absolute max. What's the lowest y value? -1. So some textbooks would place their max and mins as well as order pairs. But for us, we're just going to focus on the y value. And that's the same thing on the AP exam. When they're talking about the values, I know they don't say it, but they mean y value. This means y value. So don't give your answer as order pair. You're going to give your answer as just a y value. So you say absolute max is 16 and absolute min is -1. If you really want to include the x value, you can put that to the side, but I'm okay with you just giving me the y value. But if you give me the order pair, then you know, you're still getting the majority of the points, but I'm going to take a point off because I'm looking for the value and not both things.
So why is that you throw in the value, not the x as well?
Think of this as if I were asking you, what is the highest and lowest height? Right? If I use the word height, then it makes more sense that you would use 16 and -1 and not time, right? If it was like a time and height function, then but yeah, so I wish College Board would be more specific and just say y value, but then they're always using the word just values. So I want to just kind of get you guys in the habit of thinking, okay, that's asking about the y value. So I have to just adjust my mind to know I'm looking for the y value. Yeah. You don't have to. You can, if you do, it's fine, but just make sure you don't put it in the order pair. If you do, then show me that the emphasis is on the y value. Okay. But if you leave the x value out, I'm okay with it. Just not the order pair, because then you're giving me equal weight with both numbers, and it's the y value that we're after.
Why did you pass the parentheses then?
Just to say that you don't have to include that. But if you do, I won't take points off if you just show me that the emphasis is here and not here. But with an order pair, I can't tell. So yeah.
So for the on 0 to 2, we have to test all of them.
We have to test the endpoints and any critical point that lands between. So we always test endpoints. Okay, we always test endpoints.
So if it's like 0 to 10.
Then you'll test 0, 10, and whatever critical point you find in between. Okay. But you're not going to test every number because you're only going to test numbers that show up in your critical point list. All right, any questions with that process? Okay, let's look at number 2. All right, our function is x minus 1 to the 2/3. This looks a little bit more complicated. There is no issue with continuity because if I plug in -1, having a cube root in the denominator is okay with a negative inside the radical because it's not a even root. So odd root is okay as long as it's not an even root. So -1 to 0, doesn't present any issues here. So let's go ahead and make our statement. Our function is continuous on the closed interval. Okay, so we already know our endpoints are -1 and 0. We know we're going to test them. But let's see if we can find additional critical points. So we'll find f prime. Now, if I want to find f prime, can you recognize what rule is involved here? Chain rule. Yeah, outside times inside derivative.
How do you know it's continuous?
Because -1 is safe and 0 is safe. So, and there's no denominator. So usually no denominator is a pretty good indication.
What happens if it's not continuous? What would you do with that?
Good. Yeah, if it's not continuous, you would say the function is not continuous on the closed interval. Extreme value theorem does not apply.
Okay.
And you'll stop there.
You don't really do any like that much work on it.
Right. Yeah. That's why we always make our first conditional continuous test. If it passes it, you move on. If it doesn't pass, there's no point in continuing. Okay, outside derivative. Bring down the 2/3, subtract 1 from the exponent. Keep the inside term intact. And multiply by the inside's derivative. What's x minus 1's derivative? 1, so no changes, right? Okay, let's clean this up and see what this looks like without the negative exponent. So I'm just cleaning it up, making it into one clean fraction. I'm moving that parentheses down to the denominator, making it share the same space as the 3. Okay, so we have our f prime as clean as we can make it. Where do we find critical points? Typically, though, the general rule is we look in the denominator and the numerator. But in this case, do we see anything in the numerator? No, right? If you set 2 equal to 0, that doesn't make sense,
Yeah.
right? So nothing there. Yeah, if we don't see a variable, then there's nothing there. Denominator, though, we can find something. We'll set the denominator equal to 0. So I can do what here? That divide 3, cube both sides.
Just we find out what's undefined.
Yes, where the slope is undefined, but it's still a valid critical point. Because if it's a sharp turn, then we still want to, it's still a potential max or min. Okay, so divide by 3, cube root both sides, x minus 1 equals 0. Therefore, x equals 1. Now, is 1 a valid critical point?
No,
Why not?
it doesn't fall in between -1 and 0.
Good. So we did find a critical point. It did not make our criteria, so we remove it. But we can still, it doesn't mean that we stop extreme value theorem. It just means that we have one less candidate to test. So how many candidates do we end up having? Just 2, right? Just the endpoints. Okay, so back into the original function. Okay? Don't plug back into the derivative because we don't care about the slope anymore. We just want to find the physical location. The -2 squared is 4. And then we still have that cube root there. So cube root of 4, whatever that number is. It's not a rational number, but it's still going to be some decimal number. And then we'll test 0 as well. So -1 to the 2/3. -1 squared is going to be 1. Cube root of 1 is still 1. So between these two, which is higher? Yeah, this is a little bit higher here. So cube root of 4 is greater than 1. So this is my absolute max. And this is my absolute minimum. And if you want to just focus on the y value, I prefer that.
You just write ABS for absolute.
Yeah. Okay, the calculus is a little messier for example 3, so let's walk through that. Okay. F of x equals 4/3 x square root of 3 minus x from 0 to 3. Let's look at our condition here. 0 is safe. 3 is safe. There's no denominator. We should be okay. Yeah.
The
So
How do you?
So first off, there's no denominator, so that's a good sign. And then I also want to make sure that my endpoints aren't going to cause any issues with my radical. So if I plug 0 in for x, square root of 3 minus 0 is a real number, so that's okay. If I plug 3 in, 3 minus 3 is 0, square root of 0 is also a real number, so okay. There's no issues with a negative number inside the radical, so we're okay. All right, so make sure that we spend the time to write out our condition. So we know we have two candidates to test. Now we want to look to see, do we have any additional candidates from the critical point list? But to find the derivative, what's involved here? Product and a little bit of chain. Yeah, so let me get it all nice and set up here.
So we're gonna define like second derivative.
No.
Okay.
Just first derivative. So I'll treat the 4/3 x as my f, and then the next part is my g. Okay, so product rule, f prime g plus f g prime.
In this case, you do product proportion.
That's right. Yeah, and here's a quick way to tell whether you want to do because like how do we know which one is which? You look to see which rule affects a larger portion of the problem. So the general rule of thumb is if parentheses is over the entire thing, then chain rule comes first. If the parentheses is only over a portion of the problem, then that means there's a larger rule at play. So the parentheses is not over everything, so that means the other rule is gonna be first. Right? You want to apply the rule that has a larger reach first. Okay, so we know that product rule comes first. And then once we get into the parentheses, we can worry about the chain portion. Okay, f prime, what's 4/3 x's derivative? Okay, g function, no changes. Okay, back to f. G prime, so now we got to go through chain rule here, right? So outside is the parentheses of the 1/2. The inside is that 3 minus x. Take turns with each derivative. Okay, took care of the outside. Now the inside becomes what? Okay. It's a little messy here. We're going to have to see how they look separately, and then we may have to merge it together into one fraction. So, okay, so let's see. I have 4 3 minus x to the 1/2 over 3. That's my first term. Plus. I'm going to clean up along the way here. The 4 and 2 can reduce. The negative I'm going to pull in front. So I have negative 2 over 3x. I'm also moving that radical to the bottom. So I'm just trying to do all my cleanup stage term all in one step. So the 4 and 2 becomes 2. The 3 goes to the bottom. The x is up top. Sorry, the negative gets dragged in front. So I need this to be a minus sign here. And then I push the parentheses back down. Okay, so everybody see all the things that I tried to do here in one step. Mhm. So the 4 and 2 cancels out to just be a 2. The 2 is in the numerator, the 3 is in the denominator, x is in the numerator, the negative is pulled in front. And then the negative exponent, I'm making that 3 minus x come down to the denominator.
Why does that x stay in the numerator and not stay the denominator?
Say it again?
Why does that x stay in the numerator and not go to the denominator?
Because if you see a variable by itself, there's an understood notion that there's a 1 underneath it. So if you see just anything by itself, that's assumption is that it's a numerator, and then if you want to see a denominator, you can put it divided by 1. Okay, now I want to find critical points, but it's hard to do without these two being in separate fractions. So I need to find common denominator to get them to be the same fraction, especially if I'm adding two different fractions with two different denominators. What's my common denominator here? Good. I need both of them. It's going to be just this right here. This is going to be enough for both to go in. So okay, I'm going to balance my fraction here. So this 3 is missing this portion, right? So I need to multiply the numerator by 3 minus x to the 1/2. So it's basically this times these two. Now, these are basically square roots. So square root of 3 minus x times square root of 3 minus x is just going to be 3 minus x. So that cleans up nice. Is the second fraction, is there any changes?
No.
No, so just 2x here. Okay, so that cleans up nice there. So I have 12 minus 4x minus 2x. Put all that under one fraction here. Okay, so this is my f prime, all nice and clean. And then from here, we can find my critical points. Everybody see how I got to the two denominators to match, push the numerators together, combine like terms. Okay, so where do we look for critical points? Yeah, numerator and denominator.
Is that part of your answer? Like that, I thought part of that.
Well, this is the cleaned up version of f prime where we can begin looking for critical points. Before this, it's really hard to do it without knowing with the fractions not being resolved. But now that f prime is nice and clean, we can look for critical points. So numerator equal to 0, denominator equal to 0. Okay, so 6x equals 12, x equals 2. Here, divide by 3, take the square root of both sides, solve for x equals 3. All right, so out of this list, do we have any new critical points to add to our candidates list? Just a 2, and then the 3 is a duplicate, right? So how many numbers are we going to test in total? 3, yeah. The 2 endpoints, and then in this case, we have an additional critical point. And how do we test them? Original, yeah, original. So f of 0, f of 2, f of 3. And then we focus on the what? When we make our statement. Focus on the y value, yep. So if I plug 0 into the function, I get 0. If I plug 2 into the function, I get 8/3. And then if there's a tie, then it's okay, just that is still the lowest y value, right? So the highest y value is 8/3, lowest y value is 0, the x value is not. We can leave that out.
You don't say like absolute max value, you say absolute max.
The implication is value, but yes, you can put value here, thanks.
Dude, why did you circle like the final simplified functions or like, or,
Over here,
yeah, no.
I just wanted to make sure that this is where we look for critical points.
Okay.
Yeah, so I guess I'd have to put a block around it. I don't want to give the,
That's like, that's not part of your final answer though, right?
it's not, yeah. I just wanted to make sure with all this mess here, I want to point out this is where we look for our critical point. Okay, so I just want us to get comfortable with this. Nothing new after this today. I just want us to practice with these concepts here.
This is
So-
a complicated one.
There is going to be a quotient rule that's going to come up, but let's go to page 3. And let's see. Why don't we try we try number 24. Okay, remember your condition comes first. And then after 24, we will try 26. Okay, that's it. We'll do 24 and 26. Okay, so our function is continuous on the closed interval. We do power rule for derivative. Yes.
Why is it continuous if there's a negative?
Right, so normally this would be an issue, right? But what do you notice about this radical here? It's cube root, so it's
Oh.
okay. If it's an even root, we have an issue. But odd roots, negative numbers will not present a problem.
Anyways, do you plug that into like the,
Yeah, well, first thing is there's no denominator, so that's usually a good sign. And then if both my endpoints work, then I know I don't have any issues.
you plug them both in X?
Yeah, cube root of -8 is safe, cube root of 8 is safe. And also, as soon as I see that cube root, I know I'm safe. I don't have to worry about, okay. What if there's a negative inside, right? That's not, we have to worry about. Right, so function is continuous.
Change the X, the one, like, to the power of 1/3.
Say again?
You're gonna change the X to the power of 1/3.
Yes, that's right. We're gonna get it ready for power rule. Now that we have our endpoints established, we're going to try to find additional candidates. Clean this up. Where do we look for critical points? Denominator. This case, numerator doesn't have any, right? But the denominator does have one. Divide by 3. Take raise both sides to the power of 3/2. I still get x equals what? 0. Is 0 a valid critical point? Yes, it lands inside. So how many points are we going to test? 3. Back into the original. Hey, absolute max value is
8. Or 2.
2. Absolute minimum value is,
Yeah, 2.
yeah, focus on the y value.
You don't worry about the middle point.
Yeah, that's true. Why do we not worry about the 0?
Absolute max.
That's right. Yeah, we only care about the absolute max and absolute min.
So is on the top is g of x is continuous, right?
I'm sorry?
At the top you put g of x.
Yeah, g of x. Yeah, g of x. Yes.
How did you get, x equals 0, like, I don't, like, how did you, like, you divide the 3 and then when you.
Right. Okay. So what I did was I divided the 3. So I'm left with x to the 2/3 equals 0. Okay. And then if I want to get rid of that, I can just raise both sides to the 3/2. So that cancels out to be x to the first power equals 0 to the 3/2. Sorry. Which one? Okay, let's last one here, 26. Thank you. All right, 26. We have to make a statement about continuity. Now, we do see a denominator here, but are we going to have any issues with continuity?
Oh, because of the denominator.
There's a denominator, but is there anything that could cause this to be
Because it's
0?
squared, no.
Yeah.
Unless we're dealing with imaginary numbers, right? But here, anything that's squared is going to be positive. Anything positive plus 1 is still going to be positive. So there's never going to be a 0 that could be here, right? So we're safe, right? So there's no continuity issues here. -2 is safe, +2 is safe, everything between is safe.
What if it creates a negative value? Would it still be continuous? Then
No, sorry, negative value is okay, as long as
it's not 0.
0, right? So if anything can cause the denominator to be 0, then we have an issue, right? But if I try to solve for x squared, I'm going to get something that it's unsolvable, right? So no issues in the denominator, but make sure we make our claim. Okay, so we have 2 candidates that we're going to test. We want to look for more. So we have to find what? Find f prime using what rule? Quotient. Okay, so there's my f prime. Okay, where do I find critical points? Numerator, denominator. But in this case, is my denominator going to give me anything? Nothing, right? If I set x squared plus 1 equal to 0, I'll get x squared equals -1. Square root of a negative value is imaginary, so nothing there. Just the numerator will help us find them because we're only after real number values, right? So 2 minus 2x squared equals 1. You can do something else different than me. You can set them both equal to each other if you want. Divide by 2, take the square root. Either way, you'll get plus or minus 1. Are both these valid? Because they're within the range. Okay, so how many candidates are we going to test? 4. And they all get inserted back into the original. Yeah. So we know we're going to test -2 and 2. We know we're going to test -1 and 1. They all get inserted back into the original function. And then we gather their y values. For -2, we get -4/5. At 1, we get 1. At -1, we get -1. At 2, we get 4/5. So if you look at all of our y values, our highest y value is +1. Lowest value, y value is -1. So that's your absolute max value. Okay, check your calendar for your homework. I put all the homework pages inside your packet. All right, come get your phones.
Everyone that involves like pushing rule, integral.
Yes, but it would look like this. Probably not though, but it would look like this. Yeah, if you see any parentheses inside the fraction or fraction involving parentheses, that's usually quotient and thing.
Did you have the calendar already?
I did, yeah, it's in your packet too.
Oh. Oh, this is on my birthday. This is on my birthday.
It's on your birthday.
Did I possibly take it the day before?
Like that 27?
26.
26, yeah.
27, that's my birthday.
Got it. Yeah, I am finishing up. They should be in the grade book by tonight. I hope. Almost done.
Yes. Oh.